Okay, here we go. So check this out. We got a lesson in general relativity. It's going to be easy. There's no math or anything. All you got to do is just follow the conversation, and you'll understand general relativity better than a lot of scientists. And so, because I wrote this paper, and if I can understand it, anybody can understand it. Just that I spent the time thinking about it, and so it should be easy to explain. This is the first time I'm going to read it. First time I'm reading through it. Let me go ahead and add it to the stage here. I'm going to put myself over here. Okay, so there we go. Now, hopefully this is clear enough to read. I don't know why it was so hard to get it to work. Whoops. Anyway, this should be easy to understand. Okay, the apparent superluminal motion in intergalactic voids, a relativistic perspective. See how well Grok understood the rate of causation, changing rate of causation. Observation of phenomena such as relativistic plasma jets and intergalactic voids often revealed apparent velocities exceeding the speed of light. This is when they observe an explosion in space or a plasma jet in space and they measure how fast it's moving. And I remember this a while back, several years back too. They would say, oh, it's going faster than the speed of light. Well, obviously, it's not going faster than the speed of light. They call it apparent superluminal motion. Superluminal motion means it's faster than light, but it's an apparent superluminal motion because it can't go faster than the speed of light, but they're measuring it going faster than the speed of light. So what's the problem here? There's a problem. So we got to figure out what's going on here. This is the abstract here. Speed of light is 186,000 miles a second. This paper argues that the superluminal appearances arise from applying the space-time metric of our galactic reference frame, influenced by strong gravitational fields within the Milky Way and solar system, to low gravity voids where the spatial metric is expanded and time dilation is minimal. Yeah, in other words, time is going a lot faster and the metric is expanded. Yeah. The resulting faster rate of causation in voids driven by the reduced presence of matter causes light and objects to appear to traverse vast distances rapidly when measured from our frame. So when you look out and you see something moving fast, or moving, and you measure it's faster than the speed of light, then obviously your measurements are off. So this leads to overestimations overestimations of distances to distant galaxies and the age of the universe, suggesting a younger cosmos. Well, it's going to lead to that, because if causation is faster between galaxies, obviously light's going to arrive faster from distant galaxies. A thought experiment illustrates the effect and implications are discussed within the framework of Einstein's general relativity. So it's all within the framework of Einstein's relativity, predicted by general relativity, as obviously explained. Because if you're going toward a black hole, anything moving toward a black hole will look to us like it's stopped, not moving, because the rate of causation is so slow. Anything away from the black hole, away from our galaxy, is going to appear faster than what things happen here. Okay, in Einstein's general relativity, this is introduction, dictates that the speed of light c is invariant across all reference frames, and no massive object can exceed it, or no object period can exceed it, object with mass, obviously, yeah. Yet, astronomical observations of relativistic plasma jets and light from distant galaxies in intergalactic voids often suggest velocities far exceeding c, sometimes by several factors of several, sometimes 7 times the speed of light. There was an actual paper that measured a plasma jet moving 7 times the speed of light, and they actually printed a paper. They had to retract it or correct it, but they actually printed the paper because they measured it with our measurements, and they didn't understand that causation is faster in outer space than it is inside of a galaxy. These apparent superluminal motions do not violate relativity, but result from a mismatch between space-time metric and our galactic frame, shaped by the strong gravitational field of the Milky Way's supermassive black hole and the solar system's matter distribution. So there's multiple observations of superluminal motion. Multiple observations, and it's not just one. It's not just a fluke. It just happens. They're always seeing this, and even when they bumped the asteroid, it shot out faster than they expected, and Oumuamua asteroid also accelerated much faster than they expected. They thought that it had some kind of energy to make it go faster. So they're trying to, because they're not using the right measurements to measure it. So anytime a scientist is not talking about the rate of causation, depending on the amount of gravity, it's showing that that scientist does not understand general relativity. This paper explores how the amount of matter, not dark matter, governs. That's very good. The amount of matter, not dark matter, governs gravitational effects on spacetime metric, leading to a faster rate of causation in voids. This causes objects to appear faster. Galaxies seem closer. No, galaxies are closer than they seem. You got to correct that. And the universe to appear younger than estimated from our frame. Because a lot of times people say stuff and they're actually meaning the opposite sometimes. I mean, it happens very often. Grok gets confused too by it. Galaxies, objects appear to be faster, galaxies to seem closer. No, galaxies are closer than what they seem. I have to correct them on that. And the universe to appear younger than is estimated by our frame. It's going to affect the age of the universe, or as measured by the time light, or the time that light takes to arrive. Because if it's going by a faster metric, it's going to arrive faster than our metric would measure. We can't use our measurements to project into outer space. Space-time metrics and gravitational effect. Within the Milky Way, particularly near the solar system or galactic center, supermassive massive black hole, the strong gravitational field driven by significant matter density induces substantial space-time curvature. The spatial metric is contracted from the black hole such that a proper distance of 186,000 miles is compressed, not just appears compressed. It is compressed in our coordinate system, and time dilation is pronounced, slowing clocks relative to a flat space-time reference, in other words, without gravity, or without any massive objects in the nearby. In contrast, intergalactic voids with minimal matter and negligible gravitational potential exhibit a nearly flat space-time metric. Here the spatial metric is expanded, making the same proper distance appear longer. No, not appear, it makes it actually longer. It is longer in our coordinates, and time dilation is reduced because it's not the speed that changes. It's the measurements of the speed that changes. It's time and distance that change. It's not the speed. The speed is always 186,000 miles a second. It's the measurement that changes. It's the miles. It's the miles that either expand or contract. And it's the time that either goes faster or slows down, which changes the actual speed, but not the measured speed. The measured speed is always 186,000 miles. So, okay. So, same proper distance appear longer. It is longer in our coordinates, and time dilation is reduced, so clocks tick faster. These metric differences result in a higher rate of causation in voids as events unfold more rapidly due to the combined effects of expanded space and faster temporal progression. Speed of light remains invariant at c. The measured speed is always the same. The actual speed is what changes. And you can't measure the speed with our measurements because the measurements are what changes everywhere in the universe. As the spatial and temporal components of the metric adjust covariantly to preserve this constant in local measurements and in distant measurements. However, when velocities or light travel times are calculated using the galactic frames, compressed spatial metric, and slower clock, using our galactic frames, compressed spatial metric, and slower clocks, significant distortions arise. So that's where you get the anomaly of the superluminal motion. The apparent superluminal motion. Consider a relativistic plasma jet in an intergalactic void. In its local frame, the jet's velocity is subluminal, but when measured from our galactic frame, the expanded spatial metric makes the proper distance appear vastly larger, and the reduced time dilation makes the time interval seem shorter. This results in an apparent velocity. Okay, and it gives you some math there. It's overestimated coordinate distance. Is it delta or something? I don't know. I figured it out. I don't even know the math. The underestimated coordinate time often yielding something different than c or greater than c. Okay, for example, some jets appear to move at several times c as reported in studies of active galactic nuclei. Similarly, light from distant galaxies propagating through voids with minimal intervening matter experiences negligible gravitational delay. Okay, the faster the rate of causation in voids due to stretched space and faster time causes light to appear to traverse vast distances almost instantaneously when measured with our galactic frame slow clock. In other words, we measure time by our clocks, but in our measures of distance inside of our galaxy. Outside of the galaxy, it's not the same rate of time, and it's just not the same measure of distance. Because if you get away from the gravitational force, the gravity of our solar system and our galaxy and our supermassive black hole, if you get away from that, that's when time goes faster, distance expands, which makes the speed in our measurement appear to be much faster. So light is actually arriving much faster than what we think it should arrive, because we don't know, we're not using the right measurements to measure it with. This leads to overestimations of proper distances to galaxies and their light travel times, inflating the perceived age of the universe. So what happens is that you look at if you look out into space, you're looking at a degree or what they call milliseconds of a degree or whatever, just like a small degree. You're looking at that measurement, but you're using our measurements to project onto the galaxy what that distance is supposed to be. And you can't do that, because away from, as the plasma jet moves out away from the galaxy, the measurement is not going to is going to expand, making it less distant. So we're measuring, say, 7 distances, when in fact it's only 1 distance. So we're using our measurements to project into outer space, and we're measuring 7 distances, but it's actually 1 distance. So keep that in mind, because when we do the thought experiment, it's going to make sense. This leads to overestimations of proper distances to galaxies, and it's going to affect the distance between galaxies as well, of course. To illustrate, let's do a thought experiment. Consider a proper distance of 186,000 miles. It's the distance light travels in 1 second at c, 186,000 miles a second. In the galactic frame, where the gravity from significant matter compresses spatial metric, okay, in the within the galactic frame, within our galaxies, we're going to hold our hands together. This is be the regular measurement. You hold your hands together or close together to represent the distance of 186,000 miles. So you hold and you count 1001. You know how you count 1001? That's 1 second. That's our second and our measurement of 186,000 miles. Only for illustration purposes, we're just holding our hands apart, close together, and saying that's 186,000 miles. Okay. At the normal pace, simulating the slower clock due to gravitational time dilation as light crosses this distance in 1 second. In a low gravity void where the spatial metric is expanded, spread your hands farther apart to represent the same 186,000 miles because remember, distance expands, so you expand a distance in outer space, the distance is expanded. This is, of course, just an illustration to make you realize what's happening. Okay, it appears larger in our coordinates. Yeah. So like I was saying, to us it looks like 7 measures of distance, but it's actually 1 measure of distance. So count 1001 faster. Instead of saying 1001, you say 1001. Because that's the faster rate of time, reflecting the reduced time dilation of the voids and faster clocks. Light still crosses this distance in 1 second locally, maintaining c. It's still 186,000 miles, but it's the measures of time and distance that change. So instead of 1001, it's 1001. So you can see it's a lot faster. 7 times faster, even still near the galaxy. Still near the, it looks like it's almost just the outer edges of the galaxy is what it looks like, but it's actually very far out from the center of the galaxy. 7 times the speed of light. Faster, if we're using our measurements, but we're not using, you can't use our measurements in outer space because with less gravity, you have different measurements. A mile, 186,000 miles, instead of being this big, is now this big, 7 times bigger or whatever. So, the 1 second is a lot faster. Both changes compound to make the speed even faster. So you're going to have to cross the same distance, 186,000 miles, a lot faster to get from point A to point B. Because if it's here, you don't have to go so far. It's just 1001. But here, you got to travel the same distance, but you got to get to, in order to maintain the speed of light, you're going to have to go 1001 in order to maintain c. Otherwise, it's not going to be the same speed of light. Okay, however, a plasma jet or light from distant galaxies measured with our galactic frames compressed ruler and slower clock appears to cover this large coordinate distance in less coordinate time, yielding an apparent superluminal speed. But it's not apparent, it's actually faster. It's actually faster if we use our measurements. It actually is faster. That's why they measure it to be faster, because it is faster by our measurements. It's really not that hard to understand. For galaxy light, the rapid transit through voids makes arrival seem nearly instantaneous by our measurements. Okay, I accept that. They seem instantaneous. Well, they are instantaneous by our measurements, suggesting galaxies are closer. So they are closer because it's the same 186,000 miles. If you use our measurement, it looks far away, but it's actually closer. because that's the same 186,000 miles is expanded, but it's still 186,000 miles. So one unit this big is now this big. So 1 mile this big is now this big. 186,000 miles this big is now this big. It's easy to understand. Okay, cosmological implications. The faster rate of causation in intergalactic voids driven by minimal matter has profound implications. With negligible gravitational potential between us and distant galaxies, light propagates through an expanded spatial metric and faster temporal progression, arriving sooner than expected because it's actually going faster than our measured speed. Our galactic frame, with its compressed spatial metric and slower clocks, overestimates proper distances and light travel times, leading to an inflated estimate of the universe's age. So it just does away with the time-light problem right there. Because between galaxies, the gravity effectively is canceled out from the pole of two objects. The gravity's being canceled out. So there's basically no gravity in between galaxies. In reality, galaxies are closer. So this is the point to consider, is that our black hole in our Milky Way is actually farther away from us than the most distant galaxy observed by the James Webb telescope. I can repeat it again. Our black hole, the center of our black hole, is farther away from us because it's so far away, we can't even see into it because it's so redshifted, so far redshifted we can't see looking into the black hole. It's so far away we can't even see that far away to the center of our black hole. So that the center of our black hole is farther away from us, is literally farther away from us than the most distant galaxy observed by a James Webb telescope. Because we can see, not with our naked eye, we can't see because we can't see infrared. But with the James Webb, you can see infrared galaxies, but you can't see into the black hole because it's too far away. Okay. And so the light, anything coming from a black hole is just too redshifted. We can't possibly see it. In reality, galaxies are closer, and the universe is likely younger than inferred. But that's a profound thing, because we think of the Andromeda galaxy as far away from us, when in fact our own Milky Way black hole is farther away from us than the Andromeda galaxy, which nobody ever talks about, but it's true. That's the implications of general relativity. That's the result of general relativity. And we know general relativity is true because we've observed time dilation. We've observed clocks move faster and slower. And with the interferometer, we have now measured the dilation of distance, the changing of distances. That's what a gravitational wave is. It's the changing of distance. It's, if you think, you got to just think about it. Just do the thought experiment and you'll understand it. So, conclusion, the apparent superluminal motion of objects like plasma jets and the rapid arrival of light from distant galaxies from distant galaxies stem from applying our galactic space-time metric. Well, you're applying. That's why it seems faster than the speed of light, because you're using our measurements to measure it with. But it's not actually moving faster than the speed of light. That's what general relativity predicts. That if you carry out the thought process, you can understand why things are moving faster in outer space. And it's the same thing with the spiral arms that are moving faster than expected. Everything moves faster than expected with less gravity. So the spiral arms, outer spiral arms of the galaxies are moving faster than expected because you're not understanding the difference in the amount of gravity as you go toward the outer edges of the galaxy. There's less gravity, means causation is faster. Things happen faster. And I mean, this stuff is so simple if you think about it, but nobody ever talks about it because nobody understands it except for the few people that do. Some people do understand it. The expanded spatial metric and reduced time dilation in voids create a faster rate of causation, making events appear to unfold more rapidly when measured from our frame. This leads to overestimations of distances and light travel times, suggesting a younger universe. So there's no need for any dark matter, invisible matter. You don't need invisible matter. That is a huge blunder. They talk about Einstein making blunders. Einstein talked about the variable speed. He actually talked about the variable speed of light, but nobody understood what he was talking about. But this saying that the universe is made up of dark matter and dark energy, no, it's not. No invisible matter, no invisible energy is needed. According to general relativity, it accounts for everything. Of course, they base the dark energy on the redshift, which the redshift is just that the amount of gravity from a distance for the pole of all the galaxies in the distance is a lot greater than the pole of gravity from our galaxy. So what happens when light leaves the galaxy? So the light leaves the galaxy, it's redshifted, and then when it enters the galaxy, it's blue shifted, or coming towards us, it's blue shifted. Now, if you're looking toward a black hole, it's redshifted because it's actually farther. But I just want to make sure I have that right. When it leaves a galaxy, it's redshifted, and when it enters a galaxy, it's blue shifted. So all things being equal, the light will be redshifted, then it'll be blue shifted back so that we can see it. Except that if our galaxy is smaller, which our galaxy is smaller than most of those galaxies, the redshifted galaxies anyways, because that's why we can see them, because they're more massive, a lot of them. But even besides that, the amount of mass out there is greater than the amount of mass in our galaxy, which will blue shift the light back to its original spectrum. You know, you don't need any dark energy. You don't need any dark matter. You just need to understand relativity and what's actually happened with the changing measures of time and distance. because it's the changing measures of time and distance that redshifts the light in the first place. And then the measures of time and distance change it back so it's blue shifted again so that we can see it. It's not that complicated. These findings, rooted in Einstein's general relativity, highlight the importance of accounting for space-time metric variations in cosmological observations and underscore the dynamic nature of the universe. Very good, with a few mistakes. I had a few mistakes, but I just had Grok write the paper the other day after I explained it to him so he could understand, but he still made a couple of mistakes where it appears to us to be moving faster than the speed of light, because it actually is moving faster than our measured speed of light. But it's not actually breaking the speed of light because it's moving by the measurements in outer space, which appears to us to be moving faster because it is moving faster. But it's not breaking the speed of light because the measurements are different in outer space. It's really not that hard. You just do this thought experiment. Do the 1001 experiment of 186,000 miles. 1001, see how fast that was? Then 186,000 miles with a 1 second as fast as you can, 1001. And you can see the speed is actually faster. It's not that hard to understand. So anyway, that's about it, I guess. There's Dwayne. Hello, Dwayne. Oh, so that's good enough for today, just a half an hour or so. I don't like to make boring videos, but it is a very important video. So there's that. So we'll just go ahead and remove this. And we're good. All right. So my latest thing is to pray without ceasing. Pray without ceasing. And stay close to God, which I always said before. Stay close to God and He'll draw near to you. I don't know if it looks like I'm freezing up a little bit, but anyways, God bless everybody and take care.